Okay, so in this next section of our energy and heat unit, what we want to do is actually shift gears a little bit. We had already talked about energy and then temperature, and we kind of left off with converting temperatures from one form to another. Now we want to talk about a related topic, which is heat. And sometimes heat and temperature are often, confused. I have the hiccups here. So, in order to talk about heat, we actually have to talk first about thermal energy, because thermal energy and heat are actually more closely related than heat and temperature are. What thermal energy is, it is the total energy, both kinetic and potential, of the actual particles in the substance. Now, this may sound like the definition as well of mechanical energy, but remember, mechanical energy relates to an object. This is actually dealing with the particles, either the atoms or the molecules. Now, this sometimes is called internal energy, and all substances have this internal energy. One way to think about it, though, is to look at this question: what has more thermal energy, a large bowl of warm water or a red-hot thumbtack? Now, there are several factors at play here. We don't have an instrument that can actually measure thermal energy. We do have an instrument that can measure a portion of thermal energy. We have an instrument that actually measures the kinetic energy of the substance, which is temperature. But we don't have anything that can measure the potential energy of the substance. So that makes it very, very difficult. There's also a couple of other things here. First of all, we have different temperatures involved, so we have different kinetic energies. But the other thing that you may notice is these two objects are much different sizes. If you think of a bowl of warm water versus a thumbtack, each of those have very different masses. So to try to answer this question based on the information provided is very difficult, because obviously the mass and the specific temperatures at which they are going to influence this amount of thermal energy. So how does this relate to heat? Heat is the flow of this thermal energy as it transfers from one object to another. So you can actually think of heat as actually thermal energy in transit or moving. Thermal energy always moves from a higher temperature object to a lower temperature object. And we actually see this with something as simple as putting an ice cube in an ice cube in a beverage. What happens is the liquid that the ice cube is placed in actually has the thermal energy flow to the ice cube itself, which causes the ice cube to melt. But at the same time, then, because it is losing heat to the ice cube, the temperature of the drink actually comes down. So, if we have a large bowl of warm water sitting on a table, does it contain any heat? And the answer to that is yes, because if it's warm water, it's sitting on a table which is at a different temperature than the water. So yes, it does contain heat, because the thermal energy is actually flowing from the water to the bowl to the table. Now we're going to, in a minute here, get into some calculations with heat. And heat is measured in a little bit different units than what we have talked about so far. The main unit we are going to be using is the calorie. A calorie is defined as the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. Now, this is not the same calorie that you would see if you picked up, let's say, a candy bar and took a look there and tried to see how many calories were in it. That is a different calorie. That is actually what we call a kilocalorie, or a kcal, and that is equal to 1,000 calories. So if I have 1 kilocalorie, then I have 1,000 calories. And you can see it's also written as a capital letter C. This is actually the unit that we use in our nutritional labels. So, and you can see that in the definition. It is used to determine the amount of heat needed to burn fat, or to burn basically the macronutrients that are present in a piece of food. Calories, though, and joules are related. We're just not going to really work with the joule here in this portion of the unit. Okay, 1 calorie is just basically over 4 joules. So if I have 25 calories, I have about 100 joules, just to give you a comparison. Now, there is another measure of heat, and you see it at different times of the year. In the winter time, you will see this when you look at space heaters. In the summertime, when the stores have the air conditioners out, you will see it. This is called a BTU. A BTU stands for British Thermal Unit, and it is equal to the amount of heat required to raise the temperature of 1 pound of water by 1 degrees Fahrenheit. So the higher the BTU output on something like an air conditioner or space heater, the more heat output it will produce, or the more cooling capacity it has. On the flip side, it also tends to use more energy, so it actually will cost you a little bit more to use some of those more those higher BTU output ones. So, how do we actually calculate heat? Well, calculating heat involves a quantity that we call specific heat capacity. And the best way to kind of talking about specific heat capacity is to give you an example. You go to the beach and you get all your stuff down onto the beach, and your mom realizes that she forgot something back at the car. So she sends you because she doesn't want to go herself. So you get back to the parking lot and you realize that you didn't bring your sandals with you to walk across the parking lot to get to the car. Now, you know that if you walk across the blacktop of the paved parking lot, that your feet are actually going to get really hot because that asphalt is very warm. But if you walk on the painted lines on the asphalt, chances are they're going to be a lot cooler than the asphalt itself. And a lot of you may be thinking that's due to the difference in color, that the lines are yellow or white, so it reflects light, and the asphalt is black, so it absorbs. And that's not completely the case here. The bigger reason why the asphalt absorbs more thermal energy coming from the sun, because remember, each of these things are in the same they're receiving the same amount of thermal energy from the sun because they're in the same environment. So the reason why the asphalt is at a higher temperature than the lines is because they're made of different substances. And those different substances have a different specific heat capacity. So what specific heat capacity is, or specific heat, it is the ability of a substance to store thermal energy. So you can think of it as how easily or how quickly a substance is going to absorb that thermal energy and store it within it. Different substances are going to absorb that heat in different ways. And we can see that with that example there of the asphalt and the painted lines. Now, there are some factors which influence our specific heat, and that is the size of the atoms, the density of the substance, and how the atoms are bonded. All can work together to affect the absorption. Now, in this class, you're not going to have to worry about actually calculating that and taking those different things into consideration. I only simply point them out so that you understand some of the things that actually go into determining that specific heat capacity. And specific heat capacity is actually a number that we assign to a particular substance. Okay, so the actual definition of specific heat capacity, or we call it specific heat for short, and it is abbreviated by the letter C. It is the amount of heat, the quantity of heat required to change the temperature of a particular unit of mass of a substance by 1 degree. You can think of this a little bit as thermal inertia. In other words, how easily, remember, inertia is the resistance to change, so how easily does it change its temperature? Things that are able to change temperature very easily have very low specific heat capacities, and things that change temperature very slowly have higher heat capacities. Now, this unit looks a little funny, and I'm actually going to write it for you a slightly different way here. Get my pen up and working. Okay, it is calories over grams times degrees Celsius. And there's a reason for that unit looking that way. It actually allows us, when we solve our heat problems, to have our units cancel each other out appropriately. All right, so what are some of the effects of heat capacity? If we have a high heat capacity, we get a slow rise in temperature of the object and a slow drop in temperature. Whereas if I have a low heat capacity, I get a quick rise in temperature and a quick drop in temperature. And remember, when we talk about a high heat capacity, we're talking about a larger number, and a low heat capacity has a lower number. Now, let's talk about the specific heat of one of the most common substances we deal with, water. Okay. Water actually has one of the highest heat capacity of some of our common substances, and it is 1 calorie over grams degrees Celsius. Now, that may not seem like a very large number, but for instance, some other things have as 0.1, 0.05. They're very, very low. So water actually being at 1 is actually very high. Now, this has an influence on things like our weather and our climate because 3/4 of the surface of our Earth is covered in water, and obviously it is absorbing and releasing the thermal energy, the heat that it gets from the sun. So this plays a huge influence on our weather and our climate. Scientists think that some of this actually is influencing the strength of storms like Katrina. So we can see this by taking a look at ocean temperatures. And we're going to look at ocean temperature, water temperature, and land temperature at 40 degrees north latitude, which is pretty much about where we are. Okay. The water temperature. In the summer, the water temperature usually ranges between 75 and 79 degrees Fahrenheit, whereas in the winter, it's down 36 to 45 degrees Fahrenheit. The land temperature, on the other hand, in the summer is not typically, but because around here we're a little cooler, but in some areas it's very common for it to be 95 to 100 degrees Fahrenheit. And in the winter, if you think about this past winter, we were very cold, 10 to 20 degrees Fahrenheit. And so if you look at places that are near the water, okay, in the summer, they're going to tend to stay cooler because the water influences their weather. And in the winter, they will stay a little bit warmer than, for instance, we do. We don't have a large body of water near us because of the influence of the waters. That big reservoir is actually warming up very slowly and cooling down very slowly. But let's also take a look at timing here. If I look at the timing of our shortest day, okay, we're going to look at the shortest day. It is usually around December 20th, 21st, maybe even as late as the 23rd. That means on that particular day, we receive, in the northern hemisphere, where we were looking at before, we receive the least amount of thermal energy of any day of the year. But if we look at our coldest day, temperature-wise, it usually occurs somewhere in late January, early February. The question is why? Well, the reason why is because we have heat getting stored in the oceans. And it actually, even though we receive so little thermal energy in December, it takes a while. It is still continuing to actually warm the atmosphere and warm that air, even though the shortest day, happens in December. So it takes from that December time frame until that January in order for the ocean to release all of that excess thermal energy. And that's when our ocean temperature is at its lowest, and that's when we get our coldest land temperatures because we have the least influence at that point by the ocean. Now the flip thing happens in the summer. Our longest day is in June, but our warmest day usually happens in late July or early August. That's what they call the dog days of summer. And that's because it takes the ocean that extra amount of time to warm up to its highest temperature. Again, if you look at the typical most active time in the hurricane season, it's after that warmest time of the year, again by about a month. We get our warmest temperature days in July and August, and our oceans actually peak their temperature in September, and that's when we get the most storms. All right, so if we are actually measuring heat, now that we understand that heat capacity actually has some practical application, if we're actually measuring heat, there are 3 factors that affect heat: the change in temperature, the mass, and the specific heat. So if I'm going to put this together in an equation, it's going to look something like this. Q equals mc delta T. And Q stands for heat, M is for mass, C is for our specific heat, and the delta T stands for our change in temperature. And the way that I calculate this, remember, is I take the final minus the initial. Okay, so if I have two temperatures, I need to see which one I end up at and then which one I started with. It is okay if that ends up being negative, because if I end up with a Q here that is negative, okay, I have a positive negative, that means heat is giving off or released, and this is absorbed. So if you think about it, this one is an exothermic, and this one is an endo. And that's what that positive and negative actually tell us. So to get you started, let's actually look at your example problems on the top of your worksheet. So let me get mine here. Okay, example 1. How much heat is required to raise the temperature of 50 grams of silver from 14 degrees Celsius to 30 degrees Celsius? And it gives you the specific heat capacity of silver. Okay, so we know we're going to use that equation. Okay. Now, if you look at this, it says how much heat. So I am solving for Q. Q stands for heat. The M is our mass, so we have 50 grams. C is given to you in the problem, 0.055. Why are we not writing all of a sudden? Hang on. There we go. Just kind of calories over gram degree Celsius. And our delta T, it is going to 30 from 14, and so that is 16 degrees Celsius. So now let's plug this in to our equation. Q equals 50 grams times 0.0558 calories over gram degrees Celsius times 16 degrees Celsius. Now, this gram here and this gram here cancel, and this degree Celsius and this degree Celsius. So that leaves me with my unit of heat, which is calories. So I only put in the units on this problem just to show you this. So I'm going to multiply these three things together, and on my calculator I get Q is 44.64. But I also have to deal with sig figs. The number of sig figs here I need is 3, so it is 44.6 calories. Let's take a look at example number 2. I don't always have to solve for Q. Okay. In example number 2, it says, what is the change in temperature if a 45 gram sample of iron of a 45 gram sample of iron if 1500 calories of heat is added to it. The specific heat capacity of iron is 0.108 calories over grams degrees Celsius. So delta T stands for change in temperature, so that's what I'm solving for. So everything else should be given to me in the problem. So I have 1500 calories. My mass is 45 grams. And the specific heat is 0.108 calories over gram degrees Celsius. So let's plug this in. I have 1500 is equal to 45 times 0.108 times delta T. If I multiply the 45 and the 0.108 together, I get that to be 4.86 times my delta T. And when I divide both sides by 4.86, I get 308.6419753 is equal to my delta T. So the last thing is my sig figs. So this has to be 3 sig figs, so 309. And I need a unit here because I'm dealing with temperature. It will be degrees Celsius. Now you have 10 additional heat problems to solve, keeping in mind a couple of things. The specific heat capacity of everything except for liquid water is given to you. Remember, liquid water is there in your notes, and its specific heat capacity is 1 calorie over gram degrees Celsius. Okay. The other thing I want to point out is number 2, you have energy given to you in kilocalories. You need to change that to calories. And for number 4 and for number 6, you're given your temperatures in degrees Fahrenheit. So you are actually going to have to change your temperatures to degrees Celsius before you solve this problem, because you can't just solve it by plugging in those temperatures. It won't work, or you won't get the correct answer.